Right. Hello, everybody. Very pleased to see you here in the new year. Happy New Year to everyone. As we've said, please keep yourselves muted throughout the talk, although please unmute if you'd like to ask a question specifically about understanding something in the talk. Now, the talk today is about battery storage, and particularly in relation to the national grid and our national infrastructure, although Robin will be touching on some of the more domestic and battery storage issues as well, and you're welcome to ask more questions on that at the end. Now, Robin Redfern is a partner of Everzone, and they are renewable energy consultants. He's also previously been working in offshore wind, so he's considered as an expert both in offshore wind and in battery storage. Okay, so please ask any questions in the chat as we're going through. And as I say, please unmute and ask a question immediately if there's something specific you don't understand during the talk. And we'll be going on till 7 o'clock today. All right, welcome everybody. Robin, thank you very much. Over to you.
Hi folks, thanks for the introduction, Ed. Very nice to meet you all. I'm always slightly concerned when I'm introduced as an expert, but I fall back on the definition of an expert where X is an unknown quantity and spurt is a drip under pressure, but hopefully I'll perform better than that today. So I've got a slide presentation for you today. So I'm just going to share my screen. Hopefully it will be visible when I do so, but let me know if it's not. Let's try that. Is that all popped up on your monitors? Excellent, brilliant. So as Ed said, this is really focused around large scale grid connected batteries. There are obviously a range of different storage devices, energy storage devices we use regularly on the grid. You'll have heard of pumped storage, I'm sure, to Norway and the likes. There's also compressed air, liquid air, gravity-based storage systems, but they're apart, with the exception perhaps of pumped storage, there's a huge amount of growth, particularly at local levels in batteries. And that's why I've chosen to really focus on that today, because it's likely to be more relevant to you and potentially you'll see one of these things around the place at some point or other. And a really growing area at the moment. It's very, very current. Roughly what I'm going to cover is sort of really the why. First of all, why are we building these things? How are people making money from them? And what are they doing? What problems are they solving? It's very different from renewable energy, which is our core bread and butter in the past, because you're not just focusing on generating megawatt hours. You're now having to do more clever things with a battery. Then we'll move on to what they look like and a little bit about where they're located. Then we're going to cover some sort of technical parameters and considerations, and we don't need to go into depth on that. It's just a few sort of examples of how we think about them. And then, as Ed said, I'll talk a little bit about domestic batteries, though it's not my core area. And also Fiona asked me to cover a bit about sustainability and environmental considerations. So we're going to launch into a bit of technical stuff, because with batteries, the devil is in the detail, inextricably so. So please bear with me. As Ed said, if there's something that you really don't get, feel free to interrupt. I don't mind at all. So revenue streams and some of the problems that we're trying to solve. A lot of text on this slide, but just to say, these are the sorts of basic reasons why we might use batteries. So the most obvious and old heritage reason to have them is as a backup supply when other power supply fails. And you still get these even at domestic level. Sometimes you have battery backups in your smoke alarms quite often, even if their main smoke alarms is a really simple example. You can buy energy when it's cheap and charge up, and then sell it when it's more expensive. That is an emerging, very strong trend, as we will come to in a moment. You can prevent overloading or upgrading a system, so avoiding building more infrastructure, because you can store energy locally and charge it up slower. You can just use it to avoid wasting it. So we get some wind farms or solar projects where they don't have a big enough grid connection to be able to export all of their power. So they might spill into a battery. It avoids it just being unused. You might want to use it over a much shorter period, but at higher power than your connection would otherwise allow. And a really good example of that is a camera flash. There's no way your AA battery in your camera flash could support a big flash, but you charge up a capacitor and it can release that energy in a very, very short period of time and make a big flash. You might use it to do complicated grid services, balancing a system. And you might use it if you've got a very intermittent power source. So for example, if you're off grid. So those are the basic uses, and given that you guys are recording this anyway, you can read some of these examples later, but I'm keen to get into the content now, so we'll move on to that. But I think we'll come back to the key ones later anyway. So trading. The reason I brought this up is it's really fundamental to what a lot of these projects are doing now, and it's at the simplest level, it is charging up when prices are cheap and discharging when prices are high. And whilst we don't see it in our domestic tariffs usually, unless we're on something like Octopus Agile or something fancy like that, normally we just see a flat rate for what we pay at home in houses. But for any commercial or larger scale grid connection, you see half-hourly pricing, settlement period pricing. And over the day, which this graph is intended to represent, so there's 48 half-hour settlement periods in a day, that varies quite a lot. These prices are always obviously very indicative, and it depends on the season and so on as to what they look like, and as you've probably seen recently in the headlines, how much gas there is available and other factors like that. But ultimately, it's a demand supply problem. Like most commodities, energy is driven by demand or supply. And so we see a lot of batteries at the moment seeking to charge up when prices are very low, or even sometimes negative. There's too much generation. National Grid or the operators have got it a bit wrong. There's more generation than expected, and they're actually paid to charge up. And then they can cash in and discharge at a much higher price, usually in the evening peak, sometimes in a morning peak. And the question for the operator is really how much of that peak do they want to use? And you get very quickly towards sort of more marginal economics, and you have to weigh that up against a bigger or a smaller battery. How much more energy do you want to store versus how much more money you would make from it? So at a simple level, it's a matter of just sizing the duration of your battery to fit doing that. So that's one primary use, and I'm just checking there's nothing I'm bringing up here that I haven't already said. Yeah, well, key point for this, and we'll come back to a bit more what I mean by this in a moment, is really how we deal with what's called round trip efficiency. It's the simple fact that you'll get a bit less energy out of your battery than you put into it because it gets hot and other losses like that. So for people to make money out of this, that's a key consideration. It also, if you're doing this, you're driving your battery quite hard. You're usually running it at full power and one or more cycles every day. So it does degrade quicker, just like the battery in your phone or your laptop. Over time starts to get worse. Exactly the same applies to these big grid connected batteries. And I'll come back more. I know I'm jumping into some technical stuff early and you're thinking, what do these even look like? I want to come into that later because this is really fundamental as to why, and then we'll come into what, if you'll forgive me. So another key thing that they're used for is balancing grid frequency. Now, as probably quite a lot of you know, we run at 50 hertz in this country. Some other countries run at 60, but 50 hertz here. And in real life, it's not always exactly 50 hertz. And this is a graph actually showing from 2016 what the range of different frequencies that the GB grid operated at. So you can see actually we're very rarely well, not very rarely, but fairly rarely at exactly 50 hertz. We're usually a little bit either side, but never very much, very few beyond 49.8 or 50.2. Now, frequency is the best proxy that National Grid have to understanding supply versus demand on the grid, generation versus consumption. If the frequency starts to drop, it implies that there's a lack of generation or too much demand. And if frequency goes too high, it implies the opposite. There's too much generation or too little demand. And National Grid is very keen to keep this as close to 50 hertz as they can, because the further you let it slip, the harder it is to get it back again. And sort of out beyond here, all sorts of things start to go wrong and trip and fall away. And that's a bit about what happened back in, I don't know if many of you remember, August 2019. There was a major series of blackouts in some parts, and we lost some bits of underground and a couple of hospitals and so on. Now, there were a lot of faults that caused that, but the fundamental part was a drop in frequency, and that leading to a load of bits of network tripping off. And that's the sort of thing that happens if this gets right out of control. Now, batteries are really good at trying to prop this up. Because they're very, very fast. You can just turn a battery on. Unlike a generator or a wind turbine, you don't have to let it speed up and so on. You can turn this on instantaneously, up to full power, 20 megawatts, bang, like that. And so batteries are used quite a lot for managing this. So most of the time we're in this sort of range. Very, very occasion, you can't even see it on this graph, it's so rare, we're out in these sorts of ranges. And if we're beyond the edges of these, it's really bad news. And that just doesn't happen. Touch wood. So what might a battery do to help prevent that? Well, this is as technical as we'll get, so bear with me. I promise not to get more technical than this, but just bear in mind, this is some power output. Oh, is that a question?
Yeah, it's just one on megawatts to give us all an idea.
Thank you.
Through it, what is the power that will be going into, say, running a house or a small town or a city, so we get the idea of the size of it?
Thank you, Ed. Yeah, really good question. Let me frame that. So a kettle is about 2.5 kilowatts normally. So a megawatt is 1,000 kilowatts. So obviously the use from your house varies hugely. On average, it's usually about 1 kilowatt, maybe a bit less. Maybe with modern LED light bulbs and stuff, you might be closer to 0.5 kilowatt on average. Of course, when you turn the kettle on, it's much higher. And this is a megawatt, so 1,000 kilowatts. So on average, if you were sustaining a megawatt all the time, you could imagine that that would be powering 1,000 houses with 1 megawatt. The reality isn't like that, because when everyone turns the kettle on at once, you've got a real problem if you've made that assumption, but that's more or less it. But thanks, keep asking questions like that. That's what we need. So output power, and of course batteries, they're not just exporting, they're also importing. So below this horizontal line here, we've got imported power. So this might be, say it's a 10 megawatt project, we might be able to export at 10 megawatts up here, or import, charge up 10 megawatts down here. And on this axis, we've got what the grid is doing, the frequency. So in the middle, 50 hertz, out here, 50.5, out here, 49.5, much like the graph we looked at just a moment ago. And this orange line reflects what these projects are supposed to be trying to do to combat varying frequency. So when the grid frequency is high, there's too much generation, too little demand, they are commanded to they're actually paid to import power, to charge up at varying amounts until they hit 50.5. And at very low frequencies, they're paid to export power, discharge. Okay. And then they do, in this particular case, it's called dynamic containment, which is the main one at the moment in GB. And in the middle, they do very little. It's really designed just to show that they're still working. So that's why there's this tiny little ramp here. If we show this against that graph you saw a moment ago, you can see it's very rare that they're actually doing very much at all. But it's of huge value to National Grid because they really don't want what happened back in August 2019 to happen again. Question from someone? Penelope.
It was just Penelope joining, so don't worry.
Oh, okay. Yeah, no problem. The key thing here is that these have to respond really fast. Within less than a second, you need to be able to get all the way up here or all the way down here. And just to give you a feel, going back to the point we made about megawatts, that's, you know, these projects are quite often sort of 50 megawatts in terms of power. So that is 1,000 houses times 50, so 50,000 houses all ramping up at once, equivalent of. So we're talking serious amounts in a very, very short time frame, and that's what batteries are good at, as I'll come back to a bit more. And this is paid for by National Grid. It's a service that the providers earn money through. Okay, I'm not gonna go, I know this is a texty slide, but it's really just an aide de memoire for me, so don't worry about reading it. But what I wanted to say is bring this back to why it matters. Yeah, okay, these people can build these projects and they can earn money trading, or they can earn money with frequency response, but how does that help the world? And of course, our main interest is how does it help reduce carbon? And the answer is it very much does, but it's indirect. So with trading, the one we talked about at first, arbitrage, if you want to call it that, we are trying to help balance supply and demand. You get paid more when there's less demand, when there's more demand and less supply, and you get paid less, or even or even the flow of money is the other direction if there's very high generation and low demand. So that enables renewables to more renewables to be put on the grid. It's doing it through a market proxy rather than directly. So instead of charging your battery directly from your solar farm, the solar farm is influencing prices because it's making price cheaper, it's generating more power. So somewhere completely separate, a battery can say, oh, look, it's cheap power at the moment, I'm going to charge up. And subsequently, when it's dark, solar plants no longer generating, there is similar price signal to discharge. Now it's more complicated than that because there's also the demand profile, but over time that is a key metric to benefit greater renewables on our grid. It's done through the market rather than directly. Frequency response also has a direct benefit for renewables, and that's because both wind turbines and solar panels are what's called asynchronous. They are not running at 50 hertz. They're not synchronized with the grid. They've got all sorts of clever power electronics that gets it to 50 hertz, but there's nothing tying it to the grid. So there's no sort of locked flywheel effect, if you like, that is holding 50 hertz. And that's a problem because as we're losing more and more thermal generation, all the old coal plants, it's getting harder and harder for National Grid to hold the frequency close to 50 hertz. And so there's more and more benefit as more renewables, non-synchronous or asynchronous systems come on to have these extra systems to hold 50 hertz. So again, it's allowing more build out of renewables. So that's sort of the why we're doing this. And it's not obvious, and that's why I'm saying the devil's kind of in the detail with these projects, but it's important to understand. I'm not going to go into this much, but this is really just a quick example of a further use for batteries, which we're not seeing a lot of in GB at the moment, but we are seeing more of abroad. This is actually taken from an example I was writing about South Africa at the moment. So if you imagine that your grid or your payment mechanism at least requires a constant output for, in this case, 16 hours a day. But obviously your solar which you've co-located it with, is for a shorter period. You could build more solar than you need. You could charge up your batteries, which is this bit up here, during the middle of the day, and you can use that to spread when you discharge to the morning and the evening peak. Now, some don't do it like that. Some might just want to say, well, wait a minute, power's more valuable in the evening. I'm just going to shift it an hour and get that evening peak price, which is more valuable to me than it is during the day if I sell it as I generate it. There's various reasons why that's not really cost effective yet in the UK, but it is elsewhere, and it's complicated, so I'm not going to go into it too much. But this is a sort of case for specifically co-locating the two together, dependent on a specific revenue case. Right, okay, so that's really covered off that difficult one about why. Are there any questions before we go on to what they look like and a bit more about them physically? Stunned silence. Okay, brilliant. Right, we'll carry on then. So don't worry, there's a lot more pictures and a lot more real stuff now. We can go into what they actually look like. So first of all, the sort of basic arrangement. How do you put one of these things together? This is diagrammatic, but there'll be pictures showing parts of this later. So they are very, very modular, as you'll see. Firstly, we have a group of cells. I'll show you some pictures in a moment about what cells look like, but at one extreme, a cell is an AA battery. That's one example of a cell. You get bigger ones, you get smaller ones, and you get different shapes. But that's the fundamental point that we start from. You can then, and they do pretty well entirely, build lots of cells into what's called a module, and they're usually sort of, I don't know, half a meter wide at least, and probably a meter deep, and they fit in a rack. So you get a lot of them stuck together in a rack, one above the other. And then you might connect multiple racks all in parallel onto what's called a string. It just means onto a common wire, basically. And then you might put a load of strings in one container or enclosure, whatever you want to call it. So it's very, very modular, which makes it helpful for suppliers because they can standardize their equipment. We've then got our what's called power conversion system, which is it's basically an inverter. It converts the DC power from the batteries into AC, but we call it power conversion system, or PCS, because it works in both directions, because you have to charge and discharge. Then we have a transformer. This is the electrical symbol for a transformer, and that's just to step up the voltage to things that the grid likes. Usually on the output from the PCS, you'll be at about 600 volts, something like that, maybe 400. And here you'll often be at 33,000 volts. So your house is about 230 volts. So even here, we're usually at a higher voltage than an average domestic supply. But here we're substantially higher, about 33 kV, sometimes 11 kV. That's the sort of thing we're talking about. Then we have a load of switch gear, it's called. I'll show you pictures of that in a moment. Just to be able to isolate this from the grid and control it and make sure it's not doing anything unsafe. And then it's finally connected to the grid. Sorry, I should say that's housed in what's called a customer substation, but you'll see that in a moment. And this word DNO, just in case I use jargon, apologies, DNO, distribution network operator. So in the UK, we've got two levels of electrical infrastructure. National Grid, you'll have heard of, they're called the transmission network operator or transmission system operator, TSO, and they operate the really high voltage stuff, the massive overhead pylons, the really big stuff, usually 132 kV and above. And we also have distribution network operators, the DNOs, and they're usually they're the Western power distributions of this world that UK power networks or others. There's about 5 or 6 of them across the UK, and they're at a lower voltage, 33 kV and below, and they distribute at a lower voltage. And there's all sorts of reasons for the differentiation. So you don't really need to know that, but that's what I mean by DNO. But the key point is it's very modular. So what does it actually look like? Well, here is an example layout. This is from a drawing actually prior to this project being built. And these are big 40-foot shipping containers. You can see there's two next to each other, and they're grouped in pairs. That's not a particular requirement, just was in this project. These are PCSs, power conversion systems. There's two on each of these big long foundations. These are some transformers, and then we've got a few other odds and sods. This is a customer substation, I think, here. So fairly simple, but all quite packed in. And just to show you what this, to give you a sense of the size, this is about £25 million worth of equipment. It's a 50 megawatt project, just to give you a rough feel for things in stuff we can understand. This is actually a Google image of that same site superimposed. So, this is a double gate. This is a sort of narrow road. It's just to give you some sort of feel for size, really, just to help with that. Okay, so you'll have probably seen a lot in ISO containers like these. There's various different variations. This is actually a shed they built around some ISO containers. So those doors there are still ISO containers. They just didn't want it to look like them. So they built a shed. But we're also seeing more and more sort of bespoke, more productized solutions now coming into the market. So we're really moving away from ISO containers nowadays and seeing more specialist kit. Inside, so these three are all inside ISO containers with a central corridor up the middle. You can see their racks, just as I suggested, and you can't really see here, but there's something called the battery management system, or BMS, at the top of each of these racks, which is a sort of rack level control system. But basically that's what it looks like. It really is that dumb at this level, but there's a lot more behind the cover than meets the eye. This is then one that's not in an ISO container, but same difference. It's the same basic approach. So the cells, I talked a bit about those. The moment you get cylindrical ones like the AA batteries, you might recharge in your torch. Prismatic just means they're stuck in a box. It's the same sort of thing. Or the pouch type cells, those are what you usually have in mobile phones or laptops or whatever, because they're sort of a little bit cheaper to make if they're encased in something hard already, and you can get a wider range of different shapes and sizes. Then we've got PCSs. These are basically inverters, as I said, and they look a bit like this. There's quite a range of them. So these and these ones are actually already installed inside one end of a ISO container. And then down here we've got some transformers. So these have actually got a protective glass wall between them for safety reasons, and this one doesn't. It's about it really for that. And then I said I'd explain what switchgear looks like. So usually be located in something a bit like this, a GFRP substation, and you might get a load of these inside. And they look like glorified filing cabinets, but basically they've got high voltage switching in. And you have to have all of this kit to do it, just because if you open a switch, instead of the tiny little spark you get in your domestic switch, these throw a huge great arc. So these all have special gas inside them that insulates the electrodes when you open or close, to avoid a big bang, basically, just because you're switching such high voltages. And then you have all sorts of special relays and other protection equipment in there as well. And then of course your meters, what you actually get paid for exporting against or importing against at certain times. In terms of locations, it's almost entirely driven by a grid connection. Now, you may not realize this, but you can actually request a grid connection anywhere you like. So in your back garden, if you really wanted to, you could request your distribution network operator, your DNO, to provide you a 10 megawatt grid connection. It might cost you a small fortune and it might take 10 years to deliver it, but in theory, they have to do it. But it's hugely price variable depending on how much work they have to do it. So generally, these projects are located near substations or overhead cables that have spare capacity already there. So there's not huge costs and time connected to upgrading the network for either National Grid or the DNO, depending on what voltage you're connecting at. They're becoming really congested in the UK now, partly because of storage projects, but also all the renewables that are being connected to them and other uses. And it's a big transition for the UK grid, going away from these big central generation units of coal or gas or what have you, to a much more widespread, dispersed generation and demand. And it means that a lot of the available capacity is already booked up, and so there's now complex systems for sharing it around and trying to have systems where, well, we might disconnect you one day every year because we're not sure we can do it, but it's better than nothing sort of arrangements. Right, I went through that quite quickly deliberately because I'm conscious of time. Any questions on sort of what it looks like, where they're located, that we've just covered?
There are some questions in the chat, Robin, but I think they're all fine for the end at this stage.
Fine, I'll keep cruising through and try and make sure we've got good time at the end to cover them then.
Okay. So
now some more back to my technical stronghold, but don't worry, I think this will make sense, I hope. Shout if it doesn't. So we're going to talk a bit about some of the sort of technical considerations. So you might say, well, come on, these are square, ugly boxes, and you've already told us they contain things that aren't that dissimilar to AAs fundamentally. So surely it's just a matter of an AA or a AAA, right? What's the big deal here? Well, actually, there's a lot of devil in the detail. So first, at the most fundamental level, and a lot of my clients still wrestle with this, despite my best efforts, is power versus energy. And we've tried to illustrate this here with, you could have a very small engined car with a massive fuel tank. And that would be a great example of low power, but significant energy. It could go on and on and on for days on end, wouldn't run out of fuel, but you're only getting a little bit out. It's only going to go at 30 miles an hour. Or you could have a revved up supercharged Mustang with a tiny fuel tank, and you can go at 200 miles an hour, but you're only going to be able to do it for half an hour before you run out. And exactly the same is true for batteries. So we talk about it at a grid level in terms of megawatts for lots of power, in terms of power, and megawatt hours, how long you can run your megawatt for, to capture energy. Just the same as your utility bills will be based on kilowatt hours. It's exactly the same. It's just million instead of thousand, megawatt instead of kilowatt. So I know that's probably fairly obvious to most of you, but it's just a key fundamental, because so much of the industry is used to renewables where it's just megawatts or kilowatts, and they don't have to think about the energy because you just deliver as you generate. But there's more than that. So we've talked about power, megawatts, and those are that's really governed by, to some extent, by the batteries, but more by things like your power conversion system, your PCS, your transformers, your switchgear, and your grid connection. Most projects will be sized to deliver all the power that their grid connection will allow, or receive all the power, import all the power their grid connection will allow. Energy capacity is more a function of what revenue streams you're wanting to access. So if you want to be doing a lot of trading, you might go for more energy, a longer duration battery, more megawatt hours, because you can then discharge over a longer peak price period, or charge over a longer negative price period. Whereas frequency response, you just want to get your power out quickly, because usually the events are quite short-lived. Dynamic containment requires only 15 minutes at rate of power, which is pretty short. Most batteries in GB at the moment are about 1 hour long, so that's, if you had a 1 megawatt battery, that would be 1 megawatt hour in terms of energy. But they'll probably increase to more like 2 in the next few years as people move more towards trading and arbitrage revenue. You've also got round trip efficiency, as I mentioned earlier. So you lose some stuff in heat between importing at your point of connection and exporting again. You've lost a load of energy, fairly obvious. But the key point to a lot of these batteries is the response time. And I've mentioned this before, but really very fast. And that's to date what's set them apart from other sorts of assets, diesel gensets or what have you. I think that covers it there. Now, why is a battery like a bottle of tomato ketchup? Well, actually, it's because you have to use it a lot slower or pat the bottom as you usually do to get it all out. So you might get a battery that says as a nameplate 1 megawatt hour, but you're only necessarily going to get all of that if you use it at a low power. So say it's designed to operate at 1 megawatt, you probably wouldn't get your 1 megawatt hour if you're running it at that. But if you ran it at a half of that or a quarter of that, you'll get a lot more energy out. There's 2 reasons for that. The first reason is the top and the bottom of your state of charge range, and don't worry, I'll explain what that means on the next slide. The second is just you lose more energy through heat when you're running it hard than you do when you're running it gently. So batteries are like a bottle of tomato ketchup, and this is one of the reasons why. So here we go. The red line here, this line along here, is charging. So you're charging your battery up. We've got power, this time in kilowatts, so more like you might think of in terms of kettles, only we're going up to 250 kilowatts, so that's probably 100 kettles. And here we've got state of charge, so 100% state of charge, your battery is fully charged. 0% state of charge, there's nothing in it, you've totally run out. So if you're starting from 0%, you're charging your battery up, you can import at your full power for that battery up to a certain point. In this case, we've assumed it's about 75% state of charge. It varies depending on the battery chemistry. But at that point, you won't be able to carry on charging at rated power. You have to reduce it because of the fundamentals of the battery effectively. You reach what's called constant voltage. You can't charge at a higher voltage. So you charge at constant current, but your voltage is sorry, you have to reduce your current as you go along. So that is, as you can see, quite a dramatic fall off. And the same is true if you discharge. So if you're starting here at 100% state of charge and you go along this way, you get to a certain point where you can no longer discharge at your rated power and you have to discharge at a lower and lower power. And that's why there's a fundamental difference between what's written on the side of your battery, and this applies to domestic batteries as well. You might well get a 6 kilowatt hour domestic battery. That does not mean that you can have 6 kilowatts for an hour or what have you. It will likely mean that you'll have to run it at a fraction of that for a much longer period to get all of that 6 kilowatt hours out of it. Okay, so that was fairly harmless, wasn't it? There wasn't too many complicated bits, I hope there. But if any of you have any questions on that, we can cover it. It's a thumbs up. Thanks for the thumbs up. Okay, so final area I just wanted to cover here was sort of batteries at home, as well as some environmental and sustainability issues. So this is actually a picture I took this weekend at my father's house, who has just bought this, and it is still in the process of being commissioned, but it is connected to a load of solar panels that's on the roof. And in this picture here, this unit up here is effectively the PCS. It's an inverter, and it directs, you can't really see in this, but this shows the PV panels in. It's not commissioned yet, so it's not doing anything else, but there's a grid symbol here showing import or export to or from grid. There's the battery here, which is this unit down here that contains a lithium ion battery, which will be lots of cells, just like we saw previously. I don't know if these are prismatic or cylindrical or what have you. And it also within this upper unit is the sort of control algorithms that say, okay, let's take from the solar panels because we've got plenty of power, or let's take from the grid, or let's discharge, etc. The general control settings. And it's around the side here, so hence the funny angle. But these are the parameters. This is the nameplate on the side of the battery that I also took a photo of. So you can see here we've got 160 amp hours. Which is another phrase. So amp hour, it means you can sustain 160 amps for an hour or 1 amp for 160 hours. It's the same thing in terms of energy. And as you may recall from old school electronics, your power is your voltage times your current. So, and it's nominal voltage is 51 volts. So if I did the maths earlier because I didn't know what specs it was, but if you multiply 51 by 160, you get about 8 kilowatt hours. So this is a roughly 8 kilowatt hour system. I probably should have known that. I trust my father knows that. This will be a relatively safe chemistry. So we talk about lithium ion, but there are actually lots of different lithium ion chemistries. I'll come to this a little bit more in a moment when we talk about sustainability points. But this will be lithium iron phosphate, which is known to be a lot less susceptible to thermal runaway, which can lead to fire, than some of the other chemistries used. And they will invariably use this in safety critical things like people's homes. So if you see on the news very occasionally, and they're not common, they have happened in a few cases, a lithium ion battery fire, don't assume that that's the same lithium ion chemistry as what you might have in your home. Lithium ion has about 8 or 9 different chemistries in use, 2 of which are commonly used. So they are not all are equal. Why would you get a domestic battery? So at the beginning, we talked about why these grid connected batteries are installed. I've talked a little bit here, I'll put a few points here about why you might get a domestic one. So the first case, which is the example for my father here, is to operate alongside solar. And it's to enable you to be able to use that solar when it's dark, effectively, or at least low light, instead of just selling it to the grid, particularly with modern day lack of feed-in tariffs. Sorry, lost my words there for a moment. You'll generally sell electricity from a domestic asset at much less value than you can buy it for. So it makes much more sense to use it locally if you can than it does to just generate and sell it to the grid. So if you've got a way of storing your own energy, there is some cost saving on your electricity bill because you use that cheaper energy from your solar panels or your wind turbine or whatever for over a longer period than that generation source allows for. I've specifically picked on solar panels because they are generally a better fit with batteries, and that's because of the duration limitation. So if you imagine wind, you tend to get several days of windiness and then several days of calm, just due to the way the weather systems work in this country. Whereas sun, it's much more daily, obviously. You might have rainy, cloudy days. This one is in middle of Wales, so it's usually grey and rainy, but you get the point. Batteries are a better fit to regular charging, regular discharging, because you don't have the duration to charge up over a 3-day windy period and then discharge over a 3 or 5 day still period. So that's one use. Another might be to shift your peak demand to cheaper times. So you could have a standalone battery without solar panels. You could charge up when the electricity is cheap and discharge into your own domestic supply when it's expensive. So you're turning the kettle on at peak times or running the oven at 6 p.m. isn't costing you the earth. But that's only beneficial if you've got one of these fancy agile tariffs like Octopus Agile or something, where you're actually charged different amounts during the day. For most of us, it's just a flat rate. So there'd be no benefit. You might get some benefit, I suppose, from Economy 7 if you've got one of those meters. And then the final example I've used here is similar to 2, but really for off-grid applications. If you are in a very remote location, you don't have a grid connection, then obviously it becomes more of a necessity than a price benefit to have a battery, so as you can have power when the wind doesn't blow or the sun doesn't shine. We have seen some domestic batteries aggregated together into large portfolios, providing frequency response. So that is possible. You can do some of these revenue type services with batteries, but it's pretty rare and it's quite niche. And how you interface that with your domestic use gets very complicated very quickly. I've just put in the bottom here, could your electric vehicle provide this in future? And there's a lot of talk about vehicle to grid. So potentially, instead of having one of these in an outbuilding or in your attic or whatever, could you just, when you plug your car in the evening or perhaps even during the day, could it flow in both directions and provide some of this benefit? And that's something that's not really there yet, but is potential for the future. Okay, unless there's any specific question on domestic batteries, I'm going to quickly cover sustainability and environmental considerations, which won't take long, and then we'll go on to hopefully 10 minutes of Q&A. But if you've got a burning question now on domestic batteries, feel free. No, okay, let's power straight on. So probably what you're most likely to have heard of, if you've heard any talk about sustainability or ethics around batteries, is this one. It's Cobalt. So one variant of, or I think there's a couple of chemistry variants of lithium-ion batteries use cobalt. The common one is what's called NMC, lithium nickel manganese cobalt, and that's quite commonly used, very rarely in domestic batteries, because it is a type that's more susceptible, not commonly, but more susceptible to thermal runaway, potentially fires. But it's got a greater energy density than many of the alternatives. So it's been historically quite good in some places where you need a high amount of power in a small device. So electric vehicles use this quite a lot. I think they're now moving much more to lithium iron phosphate. But there's certainly been widespread use of this. Unfortunately, most cobalt comes from, not all, but a major proportion of it comes from the Democratic Republic of Congo. And there's lots of alarm signals about all sorts of very unpleasant practices in how it is extracted and mined. And below, you've got a table here that I've actually taken from this report, which some of my colleagues wrote, which talks a bit about it. That by far the biggest is this point on cobalt, as I've talked about, and it really quite frightening, some of the things that happen in DRC around this. Lithium, obviously, it's in the name, so everyone thinks about it. Lithium's actually a really abundant material. The problem is there's very few, or relatively few, places where it's in high concentration. So lithium, we could have as much lithium as we could ever possibly want if we were prepared to pay for it. So if you wanted to extract lots of lithium from seawater, for example, you could get bucket loads of the stuff, but it's so dilute in seawater that it's energy and therefore cost intensive to extract it. So generally it's mined from certain ores, and there it's a more trace element. So it's not rare, it's not constrained, but it is in high concentration sources. And so that's where the sort of lithium side of things are, but that's very much lower down on the sort of constraint list than cobalt, for example. And indeed, I heard recently an article about about them beginning to plan potentially some lithium mines in Cornwall. A lot of it, I think, at the moment comes from China, some from Indonesia, I believe, but it's not in short supply at the moment, but potentially could be until people are prepared to put more energy or expense into extracting it. And then graphite is it's commonplace. It's in your pencils and everything else. So I'm not sure that's such a helpful point here. The key point is cobalt can be easily avoided and already is in increasing proportion of grid connected storage applications and electric vehicles. We're moving more and more away from cobalt anyway. Lithium, not a major problem, and also can be substituted for sodium. So we are beginning to see, still really at demonstration level, sodium ion batteries instead of lithium ion batteries. So that also offers a route through. So by building this industry, we're already getting to the point where the other wider knowledge and infrastructure are being built out that the batteries themselves could potentially be switched to different chemistries in the future. So in terms of can we carry on building these things forever and a day? The answer is probably. Can we do it with cobalt and lithium? I would hope not, at least not with our current practices. And can we do it in a safe and sustainable way? Yes, but we just need to evolve our methods of extraction and the chemistries. And then finally, recycling. Very little of the world's lithium-ion batteries that have been produced in the world are currently at the end of life. Because we've had such a recent surge, the vast majority are still in use in electric vehicles and so on. So the recycling industry hasn't yet really caught up, which worries everybody, I think. But at the same time, it's not reached its heyday yet. Currently, 50% of battery content by weight has to be recycled by law. In the EU, that's being increased, I believe, quite soon in the next year or two to 80%. I don't know if the UK will follow. But it's still really focused around the most expensive elements, as you can imagine. Ironically, the cobalt containing cells are much more recycled than some of the ones with less sort of ethical concerns or lower cost, such as lithium iron phosphate, because the cobalt is so valuable. And so that drives more of the recycling. There's lots of work to improve there, both from how we build the batteries to be recycled and also the processes to do that recycling. And at the moment, I'm sad to say, I think quite a lot of them are, quite a lot of the proportion of them are still effectively lost and not in a reusable form. And that is my slide content. So over to you guys to ask any questions.
Brilliant. Thank you very much, Robin. There's a lot of questions there already. If you wouldn't mind stopping sharing the slide, and then we'll get it up onto the full screen.
Let me see if I can do that.
Okay, well, that's great. And just the things you were coming on to the end, so just to come in with a sort of general comment right at the end, or question right at the end, and then we'll start going through the chat. All of these innovations you're talking about, moving to sodium ion batteries, innovations in recycling and that, is that happening quickly enough, let's say, through market forces, or is it going to require government intervention? And I just add on to that, just a thought of, are those innovations happening quickly enough for a 2050 net zero target for the UK, and or even quicker necessarily? And if we wanted to up the target and bring it forward to 2040 or 2030, is that going to require a lot of government intervention, stick and carrot into the market?
Oh, you ask easy ones, don't you, Ed?
Sorry, that was meant to be an opener and not taking too long to answer.
Well, I mean, it's a bit of a balancing act, because some of this already comes because of regulation. The fact that 50% of batteries are recycled is already because of a requirement to do so. originally an EU requirement, which came with us when we left the EU. So that need for recycling is already there. But actually, as I said earlier, the main driver for recycling has been the value of the materials. So it's somewhat a self-regulating system. As we get shorter on resources, lithium, for example, so the value of that lithium will go up. So there will be much more impetus to recycle. Now, in terms of the build out of the overall industry, I have fallen off my chair many times at just the sheer rate of build up. So we had really the first commercial scale batteries in this country appearing, so 2017, 2018. We now have about 1.5 gigawatt hours of battery in the UK. Now, gigawatt hour is 1,000 megawatt hours. So we have huge quantities. That's a large power station, effectively, of batteries.
Just put it in context. So 1.5 gigawatts. So that would be 1.5 gigawatts supplied over 1 hour.
Yeah.
Which would what? Would that run London for 1 hour?
I don't know how many homes there are in London, but if you assume that the average home requires, on average, a kilowatt, so you'd have 1 million of those.
Right. Okay. Right. Well, that sounds like it would be half of London, maybe.
Yeah.
Something like that. Okay. Right. I'm going to start whipping through some of the questions, and please, anybody, you're free to unmute and come in with a question if it's a burning question. So Jane's asked, as recent experience has shown, markets don't always work well. How vulnerable is our supply to failing markets, e.g. arbitrage incentives inconsistent with essential consumer incentives? And how do asynchronous, if I say it correctly, renewables help or hinder?
Wow, great question. Okay, so firstly, that has been the initial cause of concern around storage, and that's really fallen away. So the arbitrage market, the trading market, they reckon is something like 13 gigawatts deep in this country, i.e. you can carry on building out to about that. That's National Grid's suggesting that in about 2030 as the depth of the market. So there's really strong appetite at the moment from investors to build these projects out. That wasn't the case 2 or 3 years ago, but now I'm getting 2 or 3 new developers every day contacting me, asking me about building out storage projects. It's gone off the scale. So really those concerns about risky markets and revenue streams have really fallen away. That used to be the case when it was all frequency response, but now that trading is really the central thing that people are looking at over the long term, there's a lot more confidence, and it's really building up quickly, very quickly.
And the idea of the depth of 13 gigawatts is that is at a level which is tradable. So if we went up to 20 gigawatts, then it wouldn't be worth getting into the business.
Sorry, yeah, thanks for the clarification. So I'm really talking about the depth before it starts massively diluting itself.
Yeah.
So the more projects you have, the more batteries you have, the more these markets self-dilute. So National Grid is saying there's room for about that much before we just don't really need it, and you've got a really smooth supply.
Right. Okay. Richard asked earlier on, and you'll know which it was referring to. How long could that kit deliver the 50 megawatts for? You were giving us some examples in the slides.
Oh yeah. So we saw a 50 megawatt project. That was a 1 hour project, which
right.
most of the GB ones are at the moment.
Right. How does that compare to a normal power station?
So
by normal, I presume you're thinking of a gas one.
Yeah. Okay. So you might get 500 megawatt or perhaps gigawatt scale. 1 gigawatt. Those gigawatts quite big. I think Hinkley is going to be 2 gigawatts, something like that. So that's a really large one. 2 or 3 is about as big as a single plant normally would be. But you get quite a lot of 500 megawatt gas power stations. If you had obviously a 50 megawatt storage project, that's quite common, but we're seeing 100 megawatt ones built out at the moment. Then that's That's obviously a fifth of a sort of good size gutsy gas power station. It's more like a tenth of a big coal-fired station, like you might see at Didcot or something.
Okay.
That's to give you some sort of feel.
And the 50 megawatt example was lithium ion batteries in that one, was it?
Correct. Yeah. That one's actually NMC, so that's got the Cobalt in it. It was an older project. A lot of them did a few years ago.
James asking what ISO stands for. International Standard something?
Oh yeah, ISO containers. International Standard. Can't remember what the O stands for, but shipping containers. Oh, thank you. There we go. Shipping containers, the ones you see on the backs of the lorries and on the big container ships. Okay,
and then there's quite a lot of different questions about electric cars, charging up and then discharging into the grid at different times. Rather than go through each question on that, maybe you could give a couple of comments. That must be something that comes up in conversation regularly.
Yeah, sure. So the biggest thing at the moment, I think, we need to work on with car charging is actually not worrying yet about discharging into the grid, because that requires a very different charger, and people to have quite clever metering, agile tariffs and all the rest of it. It gets a lot more complicated. But one thing that people can do, which is useful, is to think when they charge up. So as we get more and more electric vehicles in the next 10 years or so, I think it's going to put enormous strain on the DNOs, on the distribution network operators and the local supplies. So finding a way of managing that such that they're all spread out and charging at different times, economy 7 lives, well said, will help. Now, economy 7, it's a good example, is the most basic form you can do. If you looked at, for example, Octopus's agile tariff, they price you, is it every half hour or every hour at a different rate? So you can get more and more clever and more geeky. And obviously most people don't want to bother with that. But if you did have one of those tariffs, you can then set clever apps on your phone or whatever to start your car charger when it's going to cost you the least, or you might even be a way of getting paid to do it. So it's at the moment it's all about intelligence as to when you charge. You can also get a really good little app from ESO, National Grid ESO, that just tells you the proportion of generation at any moment. And being an energy geek, I often look at it and say, oh look, we got 42% from wind at the moment. That's quite good. But it's just fun to see it, and helpful to sort of be involved right now.
And just on the car one, then we talked about home battery installation and why you would be using it. What about your solar panels at home charging straight into your car, and then from your own car putting it back into your home?
Yeah, so I mean, it's exactly the same thing, just it's your car instead of a battery in a barn, as the picture I showed earlier. The key problem is at the moment, very few cars or car chargers are set up to work in both directions. They're really designed just to charge, not to discharge. And secondly, there's the impact on the warranty of your car or the longevity of it, because you're using your battery harder and more than the vehicle manufacturer expected. So you may find that you start getting into more trouble there. The industry's not quite there yet, but there's a lot of talk about it.
Right, I can see we've already run 5 minutes over. If you're happy, we might go on for another 2 or 3 minutes. Are you happy?
Fine by me.
Try and get another couple of questions in and that. And then if anybody who is listening has a burning question and I'm not going to get to it because I'm never going to get to the bottom of them all, then feel free to interrupt in a second or so and just try and ask your question. Otherwise, I'm going to manfully work down. Quick one, because probably one that we all think about daily, is lifespan of batteries. So probably a quick comment both about the sort of domestic installation we looked at as well as the commercial one. What's the sort of lifespan of those, and when they've come to the end of their lifespan, what happens next?
Good question. So lifespan is heavily dependent on how you use it. We're working on a massive it's over a gigawatt hour of battery, just one project at the moment in South Africa, which should easily last 20 years before it's down to a state that it sort of becomes unusable, and that's because it's being used quite gently. Its energy to power ratio is high, so they're using lots of energy over a long period and using it very low power. That's a nice gentle way to use a battery. If you're hammering it, if you're using your electric vehicle really hard, you're driving at 90 miles an hour everywhere you go, and you drain it very quickly and then you charge it up really fast, supercharger, and then you use it really quickly, you'll get a lot less lifespan. So if we see say 2 full cycles a day, that's full charge, full discharge, full charge, and full discharge, it's 2 cycles, then you might get something like 8 years before it starts to really fall away. And usually people will talk about end of life being somewhere between 60 and 70% energy capacity. So once it reaches that sort of threshold, there's a prediction that it's all going to really fall down fast from there, just like your phone or your laptop tends to get pretty bad pretty quickly at the end of life.
And is there a second life for a commercial one? I mean, there is examples of Tesla batteries and that, for instance, being then used for domestic charging. What about commercial?
Yeah, possibly. We're just not there yet. The industry is so new. I've been in this industry myself for 5 years and I'm considered an old timer. Whereas compare that with automotive or something else, I'd still be a spring chicken. So we just don't have the intel for that. Right. The expectation is that if anything, electric vehicle batteries will come into to static applications rather than the other way around, but even that's very difficult. I don't personally believe we will see a lot of that, because I think you'll use them until they're pretty knackered, and at that point hopefully there will be a lot more recycling infrastructure in place to deal with it. It's also very difficult to augment batteries, to combine old with new, just like you can't really in your TV remote, or you shouldn't.
Okay, right, a couple of quick ones. You'd mentioned lithium iron phosphate being safer in terms of thermal runaway, and Lee's just asking, is that the safest of all the types?
It's certainly the safest of the common types. I mean, there's as many different types as I've got fingers and toes, but there's significant reasons not to use some of them. For example, very poor energy density or other factors. So yes, and lithium iron phosphate and lithium nickel manganese cobalt are the 2 by far most common ones, and lithium iron phosphate is really pretty good as far as we can tell. That doesn't mean it's 100%, but you very rarely hear of any issues with it.
Okay, Nellie's asked your father's system for the 8 kilowatt hour. What's the sort of cost of it? And then just going to add on to that, so you could answer.
Wish I knew. I don't know how much he spent on it.
Okay, fine. All right. And then what about these kind of things? Could you do this as a DIY project, or is that a dangerous path to go down?
I probably wouldn't recommend that. Largely, I mean, even if you're a competent electrician, you might be able to do it safely, but there's certainly, you certainly would want, even if you were competent to do it, to install it yourself, you would definitely need to buy it as a full battery kit rather than just connecting loads of batteries up yourself, because they have quite clever control systems that prevent them reaching dangerous states of charge or voltage. And really that's fundamental to these things not reaching thermal runaway. Even the tiny little battery you have in your phone or whatever has additional wires going into it, which are responsible for controlling voltage at cell level. And you don't want to mess around with that, because it can be very bad news. You can either just stop it working quite easily, or you can get it in theory into thermal runaway, and then you've got a problem.
Right, great.
There was another question connected with that and I've forgotten what it was, sorry.
Well, if anybody wants to shout out a really burning question, if not, this is the last one then. So you mentioned sodium ion. So quick, how close are we to actually getting sodium ion going? And then also Stuart has come in and says he's heard of aluminium ion. Any comments on that? And then that'll be the end, unless somebody shouts out.
Sodium ion, there's talk about it. It's certainly been proven. At the moment, the cheapness of the sodium is a long way off offsetting the lower energy densities that it provides. So we haven't seen a sort of commercial drive to really bring it together, but it's not terrible. They're not bad. We just don't really see them at all commercially yet. It's more sort of demonstration level. So in terms of when, I think that would depend on advancements in the chemistry, overriding the disadvantages in terms of its energy capacity and other factors. I should be writing these down. There was a second question there.
Aluminium ion. Stuart,
oh yeah, thank you. So aluminium is involved in several lithium ion chemistries. So there's lithium ion, aluminium oxide, I think, and other lithium chemistries involving aluminium. I have not yet come across aluminium as the primary element of the anode yet, but that doesn't mean it doesn't exist. Most of my work is around the mainstream chemistries and integrating them with the grid rather than I'm not a chemist myself.
Right. Robin, brilliant. I'd be quite pleased actually if anybody's listening and wanted to comment, if they could unmute and just say if you thought this is the right sort of level. And that's not about Robin's fantastic presentation, but if this is the sort of level of things we should be having in the Hazlemere climate talk. So is anybody possible to unmute and say what they thought in terms of level?
Oh, wait, quick.
Can I just, that was absolutely fantastic, Robin. I am the least scientific engineering person, but it was very exciting. I didn't get it all, but I got the main theme of it. So thank you so much. And I
Thanks,
also
Jane.
very much like the cars. So that is, my husband sitting next to me, who is an engineer, said, oh no, it's not like that at all. I was talking about batteries or something, but it meant something to me. So I just thought that was really inspiring. So thank you.
Thank you. It's very helpful for me because I do get rather overexcited about batteries. And I think I'm one of very few people in the country to do so. So it's good to hear it work for somebody.
Great. Anybody else to comment? I'm particularly interested in the and I loved it, but just did everybody else find it the same as well?
Please don't feel obliged to be positive. Knock me down, I don't mind. Critical feedback's useful.
Positive and a negative, so I suppose that's anybody else? No. Okay.
My husband just wants to say
Don't get me wrong, the pictures of the cars were great, and it really showed really well a great concept. So that wasn't what he was saying. I thought it could have been misinterpreted.
No, didn't take it like that, don't worry.
And Robin, I've got a dog for you as well.
Robin, that was absolutely brilliant. Thanks very much. I mean, I loved it. Again, a bit like Jane, didn't get absolutely everything, but got 90% of it. So found it really useful. And I may well go back over the talk again myself, actually, and look at your slides again, where I can pause what you're saying while I'm checking the slides. So thank you so much. Just while everybody's on, please do come along. We're doing these every single month, as you know, at exactly the same time, 6 o'clock on the first Monday of the month. We're also looking for more participation in the Hazlemere Climate Emergency Working Party. So we have lots of projects we'd like to be executing if people would come along and join us and try and join in on that. And particularly over the next couple of months, it should be mentioned that the community boards still have money available for environmental and other projects. And if we're going to get in and get some of those projects going and paid for or partially paid for by community boards, we have to get our skates on. So if anybody has any ideas or wants to give any input in that, please do come back to myself or Fiona or anybody on the parish council or the working party to let us know. Thanks very much for attending, everybody. Robin, thank you so much again. It was brilliant. Yeah, really, really good. Thank you so much. I wish we'd had 2 hours and we could have kept talking about it. All the best.
You ask, I'll keep talking. Cheers, guys.
Cheers. Bye-bye.